Hello everyone, welcome to my civil engineering YouTube channel. Please subscribe to it and hit the bell icon to get notified when I post my new videos. Today I'll be discussing regarding how to analyze a frame using moment distribution method. So I have taken an example of a numerical of a frame, and we are supposed to analyze this numerical, and we are supposed to find out what is the bending moment, and also we are supposed to find draw the bending moment diagram. So here I have taken a typical frame here. You can just observe in a sketch. So this is a typical frame here. So wherein B and C are the joints, A, D and E are the supports. So these are the roller supports. So AB is a span which is of 4 meter in length, and which is subjected to uniformly distributed load of 30 kilonewton per meter. So BC is a span wherein it is subjected to concentrated load which is at the eccentric distance of 1.5 meter from B, 1.5 meter from B side and 2.5 meter from C end. So again we have CE span, so which is subjected to 10 kilonewton per meter UDL of span equal to 4 meters. So at the last we have BD span which is of 4 meter, and it is not subjected to any other loading conditions. So with this we are supposed to find out the fixed end moments. So our first step to analyze a frame is calculation of fixed end moments. So first thing is we are supposed to take the span AB here. So as we know that for the span AB, it is subjected to uniformly distributed load. So when the structural member, when it is subjected to the uniformly distributed load, then the fixed end moments is equal to WL square by 12. So W is equal to 30, L is 4. So 30 into 4 square divided by 12, which is of the negative variation. So it is equal to minus 40 kilonewton meter. So the next, coming on to the next span, that is MFBA, fixed end moment at BA span. So it is a positive variation of fixed end moment of AB. So that is nothing but plus WL square by 12. So it is 30 into 4 square divided by 12, which is equal to 40 kilonewton meter. So the next span here is span BC, fixed end moment. We are supposed to find out for span BC here. So as we know that it is subjected to the eccentric distance of 1.5 and 2.5 meter from B and C. So I just take 1.5 as A and 2.5 as B here. So with this, so the formula for fixed end moment, when the structural element is subjected to the eccentric loading, will be taken as WAB square divided by L square from the left hand side. So W here is taken as 60 kilonewton. So A is 1.5 meters and B is 2.5 meters. So 60 into 1.5 into 2.5 square divided by the overall length of the of the span BC is equal to 4. So 60 into 1.5 into 2.5 square divided by 4 square, we will get the value as minus 35.15 kilonewton meter. So the next fixed end moment is for span CB. So it is a positive variation of WBA square divided by L square. So here A is equal to 1.5 meter and B is equal to 2.5 meter. If I just substitute that, so it will be 60 into 2.5 into 1.5 square divided by 4 square. So it is equal to plus 21.09 kilonewton meter. So the next span here is CE. So MFCE here. So here if I just rotate the vertical part of the span CE, C will be towards the left hand side and E will be towards the right hand side, because the 10 kilonewton will be acting in the downward direction. So with that view, I will take MFCE as a negative variation. So therefore, since it is subjected to the uniformly distributed load, so from the left side, the fixed end moment is taken as minus WL square by 12. So 10 is the value of W, L is equal to 4. So 10 into 4 square divided by 12. So that is equal to minus 13.33 kilonewton meter. So similarly, MFEC is the positive variation of, this should be positive. So this is the positive variation of uh, fixed end moment of CE. So that was equal to 10 into 4 square divided by 12. So that is plus 13.33 kilonewton meter. So we are left out with the only span, that is BD, fixed end moment BD and DB. Since it is not loaded with any of the loads, so therefore fixed end moments for BD and DB is taken as 0. So next step is to determine the distribution factor here. So you can just observe this table here. So since there are two joints here, so joint B and joint C here. So as in case of joint B, with the origin from B, there are three members which are passing with B as origin. So that is BA, BC and BD. So I just repeated, when we consider the overall frame here, so B and C are the two joints. So wherein from B as the origin point, so there are three members which are passing through B. So that is BA, BC and BD. So we are supposed to find out the distribution factors for those from B as a joint. So joint, member, relative stiffness, total stiffness and distribution factor. So for joint B, BA, BD and BC. So coming on to the first member of joint B, that is BA. So here in the previous lecture series, we have discussed regarding the relative stiffness for different cases. So since A is the farther end for B, for BA member, so I just repeated, A is the farther end for B with BA as a member. So therefore, since this member A, farther end A is a roller support, therefore the relative stiffness will be 3/4 of I by L. So for a roller support, with a farther end as a roller support, the relative stiffness is equal to 3/4 of I by L. So here 3/4 times of I is constant throughout. So it is I divided by L here is 4 meters. So if I just solve it, I will get a 0.375 I. 0.375 I. Similarly, the second member of joint B, that is BD. So again, D is the farther end for B with BD as a member. D is a farther end for B with D as BD as a member. So therefore, D here is again a roller support. So wherein the relative stiffness is equal to 3/4 of I by L. So I remains same throughout. I remains I itself, but L here is again 4 meters. So it will be 3/4 of I by 4. So it is 0.375 I. So again, for the member BC here, so the third member of joint B, that is BC here. So in this case, so BC, C is the farther end of B with BC as a member. So since C is the continuous support here, so C is a continuous support. In such case, the relative stiffness is equal to I by L. So I remains the same here. L will be equal to 4 meters. So I by 4, that is equal to 0.25 I. So next, coming on to the joint C. So for joint C, with C as origin, there are two members which is passing from C as origin. So that is CB and CE. So CB and CE are the two members which are passing with C joint as origin. So therefore, the coming on to the member CB of joint C. So CB, for CB member, B is the B is a farther end. B is a farther end for C with CB as a member. So therefore, B is a continuous joint here, continuous support here. So therefore, for a continuous support, relative stiffness will be equal to I by L. So I remains constant. L is equal to 4 meters. So it is nothing but I by 4, that is 0.25 I. So similarly for CE here, so CE, in case of CE, E is the farther end for C with the CE as a member. So that is a roller support. So therefore the value will be 3/4 of I by L. So 3 by 4 times of I by 4. So that is 0.375 I. So the next step is to a calculation of total relative stiffness here, that is sigma k. I need to add all the three that of the relative stiffness of each joint. So here for joint B in concern, we have three relative stiffness. What I have got, I need to add all these three relative stiffness, that is 0.375 I plus 0.375 I plus 0.25, so that I will get the total relative stiffness, that is 0.624 I. So similarly for joint C, I have two members, two relative stiffness with two members in concern. So therefore that is 0.25 plus 0.375 I will get it as 0.437 I. So similarly, the calculation of distribution factor. So if I just take the ratio of k by sigma k, so I'll get the respective distribution factors. So for BA, I have the relative stiffness as 0.375 I, and total stiffness I have as 0.624. So if I divide one on the other, so I will get as zero point 0.3. Similarly for BD, I have got it as 0.3, and BC, I have got it as 0.4. So with respect to joint C, so with CB as a member, for CB relative stiffness I have 0.25 I, and total relative stiffness as 0.437 I. So if I just divide one on the other, so I will get the factor as 0.57 0.57, and one more for C as 0.43. Coming on to the next step, that is moment distribution table here, which is a very important step here. So member, first column is a member. So in that member, I have AB, BA, BD, DB, BC, CB, CE, and EC. So distribution factors for the joint members. So BA, since I have calculated in the previous slide itself, so same you are supposed to write it down as a distribution factors for the respective joints and its members. So BA, I have got it as 0.3, BD, I have got it as 0.3, BC, CB, and CE. So next step is fixed end moment. So I need to write down what all the fixed end moments I have got for the respective spans here. So for AB, I have got it as 40 minus 40, BA, I have got it as plus 40. So BD and DB, since it was not loaded, so therefore fixed end moments was 0 and 0. So for BC, I have got it as minus 35.16, CB as plus 21.1, CE as minus 13.33, and EC as positive variation, that is plus 13.33. Now you can just observe in the diagram here. So in this sketch here, so you can just observe here. So in this sketch, A, D, and E are the joint, are the roller supports. A, D, and E are the roller supports. So here In case of roller supports or a simple support or a hinge support, we are supposed to release the moments. So we are supposed to release the fixed end moments. So in that is nothing but we are supposed to make the moments, total moment, to be as zero as in case of hinged or simple support or roller support. So if I just take an example of AB here with A as origin, so here I have for initial fixed end moment as minus 40, and as in case of for D here, dB should be equal to 0. dB should be equal to 0. Yeah, it is 0. So not a issue with this, because since it was not loaded with any other loading condition, so it is equal to 0. So next support is support E here. So in case of support E, we have E with E as origin, the span will be EC. So in that case, we have the fixed end moment as 13.33 with a positive variation. So in order to release this positive 13.33, I need to add the same magnitude but opposite direction, opposite sign convention of the moment, so that the overall moment of that member should be equal to 0. So in such case, I need to add minus 13.33 here, and then I need to carry this half moment to the same span to the next supporting member. That is, for EC, if I just want to release the moment, I need to add half the moment to the CE. That is nothing with the same sign convention. That is, for minus 13.33, if I am going to add for EC, so I need to carry out this half of minus 13.33, that will be equal to minus 6.66 to the same span but the other support. Okay, so that is nothing but for CE I am carrying the 6.66 with the same sign convention. Similarly, coming on to the member AB, so I have said that since A is a support wherein it is a roller support, so therefore I need to release that moment by adding the same magnitude but opposite in direction. So FEM for AB here is minus 40. So in order to release that, I need to add plus 40, and then I need to carry the half the moment to the same span of the other joint. So that is nothing but I need to carry plus 20 with the same sign convention as I said. So plus 40 I have added. So I need to carry plus 40 by 2, that is plus 20 to BA. So therefore, after releasing the moment, so final initial moments I am supposed to add out. So minus 40 plus 40, it will be 0. So 40 plus 20, it is 60, and here once again it is 0. So again here is also 0. So minus 35.16, so 21.1 and minus 20, and this is 0. So these are the initial moments. So here initial moments I have got. So initial moments as I got, so I need to distribute this moment. I need to distribute this moment as per the distribution factors in concern. So coming on to joint B, with the three members I have for joint B, BA, BD and BC. So I need to add all the moments of all these three members. So that is plus 60, plus 0, minus 35.16. I need to add all these three moments, and then for that addition of all the three moments, the what the answer I will get, I need to multiply with the respective distribution factor of the members. So I have 60 minus 35.16, some amount of answer I will get. So that answer multiplied by point 0.3, if I do, I will get the moment for member BA. Similarly, so the total moment, so multiplied by point 0.3 again, so I will get once again minus 7.45. So again, total moment multiplied by zero point 0.4, I will get as minus 9.94. So here you can just observe that if I get the total moment in the positive sign convention, so in order to counter the unbalanced moment, I need to take the distribution moment in the opposite direction. So coming on to the joint C here. So coming on to joint C here, so there are two members you can just observe, that is CB and CE. So CB you have as 21.1, so CE you have as minus 20. So I need to add that both moments, that is 21 point plus 21.1 minus 20. So the overall unbalanced moment will be plus 1.1. So this is the 1.1 is the overall unbalanced moment for joint C. So in order to counter this unbalanced moment, so I need to distribute this unbalanced moment with the opposite sign convention with reference to the respective distribution factors. So 1.1 multiplied by 0.57, if I do that, I will get 0.627. So since in order to counteract with the positive unbalanced moment, I need to take the value as minus 0.627. Similarly, 1.1 multiplied by 0.43, if I do, I will get the value as minus 0.47, minus 0.47. So similarly, the next is carryover step here. So since this 7.45 minus 7.45 cannot be carried, because AB the moment are released and it is equal to 0 itself. So again, in case of DB also, the moment is released, therefore it can't be carried out, it remains as 0 itself. So once again, as in case of BC and CB, so I am supposed to carry this minus 9.94. So half the moment, that is minus 9.94 divided by 2. So with the same sign convention I am supposed to carry. And similarly, 0.627 minus 0.627 I carry divide by 2 will be minus 0.31 with the same sign convention. And again, C is the roller support, where I mean E is the roller support, wherein I have released the moment. So here in this case, I don't want to carry the moment here, since it is 0 as it is. Here in the next step, I have a balance moment. So I have a balance moment here as 0.09 and 0.09. So here it is 0.12, 0.12 and 2.83 and 2.13 here. So again, there is no carry for AB, DB and EC. Only the thing I am supposed to carry it for CB and BC by taking half of the moment. So 2.83 divided by 2 with the same sign convention. Again, 0.12 divided by 2 with the same sign convention. So I need to distribute this. So for B as a joint, BA, BD and BC as the members, I only have the moment as 1.42, so which has to be distributed for the three members with reference to the respective distribution factor as 0.3, 0.3 and zero point 0.4. So multiply that 1.42 into zero point 0.3. So it will be minus 0.43 minus it should be minus 0.43, and then this should be minus 0.43, and then minus 0.57, minus 0.57. So here why it is minus, because 1.42 is an unbalanced movement which is of the positive variation. In order to counteract that, it should be a negative value of the distributed moment. So next, for CB it is point zero point 0.06 for C joint with CB and CE in concern. So 0.06 is an unbalanced moment here. So I need to distribute for CB and CE with the distribution factor of 0.57 and 0.43. So 0.06 multiplied by 0.57, I will get as 0.03, and my 0.03 with a negative variation, since 0.06 is a positive value. So again I am supposed to carry out this. So 0 for AB, DB and EC. Only the thing is, for BC and CB, I'm going to carry that with the half of the moment, with carrying the same sign convention. So 0.57 divided by 2 will be 0.28 with a negative sign. So similarly for 0.03, divide by 2 will be 0.01 with the negative sign convention. So the overall balance will be 0.003, 0.003, 0.004, my 0.16, 0.12. So this procedure has to be repeated, repeatedly repeated, so that the final balance should be of a very smaller quantity. So till then you are supposed to continue this procedure. So at the last we'll get the total moments. We are supposed to add all the moment, carryover and balance, starting from the initial moment. So total moment at AB is 0, BA is 52.21, BD is minus 7.787, DB is 0, and BC is minus 44.44, CB is 18.25, CE is a minus 18.25, and EC is 0. So if we just observe here for joint C, so you have two members CB and CE. So wherein the moments are distributed equally with the opposite sign convention, if you just add that, the moment will be the overall moment is equal to 0 at that joint. So similarly for joint B, if you there are three members, that is BA, BD and BC. So if you just add all the three, the overall summation will be equal to 0. Therefore, there is a satisfaction of joint equilibrium condition. So coming on to the last step, that is calculation of the maximum bending moment. So as for span AB, it is subjected to uniformly distributed load. So that will be equal to WL square by 8. So 30 into 4 square divided by 8. The value is 60 kilonewton meter. Similarly for span BC, it is subjected to the eccentric point load. So wherein the maximum bending moment is equal to WAB divided by 12. So W is 60, A is 1.5 into 2.5 divided by 4. So therefore the value is equal to 56.25 kilonewton meter. So similarly for CE, so this is CE, so span CE in concern. So it is WL square by 8. So W is 10 into 4 square divided by 8. It is 20 kilonewton meter. So this is the sketching of the bending moment diagram. So as in case of AB, I just take the moments which I have got from the moment distribution table first. So here at A I have received it as 0. So at AB it is 0. So BA I have taken have got it as 52.21, and then BC as 44.44, and CB as 18.25, CE as again minus 18.25. So BD as 7.87 and DB as 0. So this is a variation. So again, upon that, if I want to sketch out for the maximum bending moment, so for AB I have got it as 60. wherein the variation is parabolic since it is loaded with a uniformly distributed load. So for BC, it is linear since it is loaded with the concentrated load with the value here as 56.25. So again, the variation for CE, it is a parabolic variation since it is loaded with the uniformly distributed load. Thank you for watching.